need to restart. Alright.
Turn the cover. Turn the cover on and off.
Yeah.
Close the cover and reopen.
Yeah, I just reconnect the cable. See if it's automatically resetting. It was okay, right? People
Still don't like mine.
so reconnect. I reconnected my laptop and then restart. Oh, okay.
Great.
Excellent.
Full screen.
Yeah. Hopefully it extends. All right. Let me start. And sorry for the delay. And today I'm happy to talk about this title. Talk about the strangely beautiful dimuons from CMS, actually from LHC today. And today is actually Christmas Eve, so I meant this talk to be very unlikely to be present during this celebrative seminar on Wednesday. So I have a lot of animations, everything, just try to entertain, try to be happy. I mean, this is Christmas. So let me start. So this is the first thing. So we know that the LHC is the most powerful client. Actually, I speed up this video by 10 times. So you see it's very fast, but this is somebody cycling the LHC. So just want to mention that the LHC is big and very powerful and supposed to find this particle. Costs like $10 US or something to find this Higgs boson. But actually we know that the people does find this, right? You know, well, this is our new CERN DG, and this is a video they took during the 2012 announcement, and they got the 2013 Nobel Prize. So, which is nice. But the biggest issue is that so far we tried many different things. This is just a snapshot of all the search have done at the LHC and the LHCMS. Basically, we found nothing. So that's all the limits. So so far we found nothing. We found no SUSY, no new extra dimensions, no new fermions, no new bosons, no black holes, whatever. So nothing new except the Higgs boson. So that's a problem. So so before actually moving forward, for example, maybe we can use this way. If the nucleus is hidden in this lock state, we want to use something like this to really open in some way. For example, you can take a look like this. So in principle, you can find new physics layer if this working, right? So, but it take a few years, I assume, or maybe it's not even enough. Maybe we need a 100 TeV machine. So not for now. So maybe you can do some more classical way of tricks. For example, you can listen to the sound given by the lock when you tune the numbers, right? So in this way, you can use some other way to open the lock and see if you have with some new physics signal. All right. So the topic of today is actually through this direction, going to so-called high precision. So basically, we have two ways of attacking so-called new physics. So one way is I say is through high energy, like you blow up using C4 or something to destroy yourself. And in principle, you can produce real new heavy particles, and you look for their decays and see if you can find them in the detectors. Or so-called through high precision measurements. For example, there can be fast precision, not necessarily very with very small error bar, but sometimes you're just looking for something very tiny, very small. For example, something like new virtual particles may enter the loop process. For example, like this, you have a loop, and these new heavy particles may enter the loop, and you can have some contribution to see you do these measurements. Maybe you can see the effects of this kind of new particles. So so the comment is that this particle cannot be found directly at this moment. This is something we can look for. Try to look for this kind of indirect hints from some super rare decay or something very high precision measurements. Okay. Okay. This is the pointers here. Okay, still working. All right. And this is the topic of the day. So we are talking about BS and BD decay to dimuons. So in a standard model, these two decays are highly suppressed. So basically, this kind of diagram is not allowed, right? This is a forever changing user current. This is not allowed. So that's why it's small. And you can only do like in this kind of either with a triangle, with a bar or a box diagram, so that heavily suppressed. So in principle, they reach to be something very, very small branch fractions. It's 10 to minus 9, 10 to minus 10, essentially. So there's two decay channel, two different kinds of B mesons. One is B sub S meson, with a composed with a B and exchange quark, and which is basically our main target today. Another one is a B and a D quark. They become a BD meson. So one is like 3 times 10 to minus 9, another is 1 times 10 to minus 10. So it's almost very, very small anyway. So in principle, you can say how small is like 3 times 10 to minus 9. So basically, people have no feeling already, right? Just like if the number is too big, you lose the feeling of numbers. When they are too small, you have no feeling. So let me give you a simple example how small it is. For example, if you remember this movie scene, this is it's around 1/3 million, 300 million actually. So it's roughly like you toss 28 coins together, and you get all of them become the same size as like a head up. So it's roughly like that. So you need to toss many, many times actually, because we need to find more than one event. Not just this is just one chance, but in principle we need to eventually to get the like a measurement. So we need like hundreds of this kind of things. So you can imagine that you need to toss many, even more times than just like 28 coins and see what happens, right? So just to give you a feeling how small it is. So then come back to the topic again. However, as what we usually you already introduced a little bit, is that this kind of small process is actually very good for new physics because they are very highly suppressed in the model, but they are statistical clean because they can be easily calculated to be high precision. And this kind of loop can insert any new particles into to some effects. For example, there's a couple examples like two Higgs doublet model or something like CMSM stuff or lepton quarks. They can actually contribute a lot. In this case, you can have like this X particle, whatever. They can maybe change the brain fashion by a large factor. So just give you an example. This is an example people usually quote. This from these references. Let's start here. This is a standard model prediction. This is what we expected the value here. And in principle, if you have like a SUSY, you can actually boost the branch fraction of the BS2 mu or BD2 mu by 10 times or 20 times bigger to this area. Maybe can happen. But so in principle, this is a very good way to calculate. If you measure something really here, you actually cut out many space. If you measure something here, you see something. Okay, strong effects. But in principle, even if it's boosted by 10 times or 20 times bigger, the decay rates are still very small actually. So it's still very hard to measure. So I think we have to go through a little bit historical things because today is a heavy day. We need to talk about something like. Well, we have measured this channel for like 30 years ago, so we have to go back to 1980s and roughly like the movie time. Okay. All right. So this was the first measurement for this. In this this is for B sub D. So this is from Cleo. This is in 1984 paper. Suppose they should see something here, but at that time actually they can distinguish pion and the muon. So actually this is sum up of pion and the muon. Then will only like 42,000 events in total, so they give a limit. So in principle, we want to measure something like 10 to minus 9 with, for example, if 20% accuracy, if possible. That means one need to produce like 10 to 10s or 10 to 11s B mesons, which is almost impossible at that moment. So even the detector efficiency is like 100%, which is not possible either. So it's very difficult actually. But anyhow, with limited data, like, at least set some limit. And this is the first measurement for B sub D, which was from Cleo, from CDF. And also the comment is that the BS meson have a 30 times bigger brain fraction compared to BD meson, but still very difficult at that time. So at that time, this is like this from CDF, and it's a 1996 paper. Actually, this is a Monte Carlo. This is the single count in the data. This is a single event they have. So basically, no single node yet. And at any time, they can push the limit to like 10 to minus 5, 10 to minus 6. And people here are actually a lot of students are working on B factories, and just show you the best result from B factories at this moment is a Baba result of B0 to mu mu. Surely there's no signal yet. This is a fail, actually have 0 count. This is all like a background sample and a single monitor only. There's no events. So at the big factories, basically people sensitive to push the limit to 10 to minus 7, and not even further, because as I mentioned at the beginning, we need to 10 to 10, so 10 to 11 is B mass, which is very difficult for B factory to reach. And so this is just like a review up to early 2012. There's one dot here means a measurement. So like is up to like early, most recent measurement from around 2000 up to now. You see many dots. So I just mentioned, a B factory cannot do better because the production concession is very too small. So we have to rely on like a hadron colliders. Basically, in proton collisions, the cross section is like 3 order magnitude higher than the E plus E minus. So in principle, we can see here, we are still like 1 order magnitude shy from the standard model prediction, which is the blue and the red curve. It's like roughly 1 order. So, and this is the best result, or kind of hint before LHC start. This was a CTF result as well, based on the almost published 4 data already. It's published in 2011, and they somehow give a measurement of B S2 mu mu, which is like 1 times 10 to minus 8, which is very big, like 5 times bigger than the expectation. But actually, this is based on 2 counts of B signal. That's 2 events, basically, 2 or roughly 2. So it's like 5 times bigger than the standard model. So you can start to comment, oh, then maybe a hint of new physics because I see 2 events, or it's just a fluctuation, which we don't know yet. But it's already at the end of the tabletron, so they cannot do further. They need more. We need more data. So it's time for LHC. So this is my topic today. So LHC. So this is a great LHC. Today, basically, we are going to talk about the results from CMS and LHCb and how we combine them together. So basically, the main topic. So this is the main campus here. This a lot of people here already staying. There's a little NTU flat here. Usually we can walk to here like 35 minutes. It's not too far. Yeah, walk to here will be much tougher, I think. So why we are not far than Atlas, right? Atlas here. So all right. So this is CMS. Just like a quick comment is that the CMS is a general purpose detector, and we have like almost 4,000 people, 3,800 people in total. And from Taiwan, we have 2 groups, NTU and MCU. So this is a detector, and you see people and the photon. And this is the LHCb. So there's nobody from Taiwan joining LHCb so far, but this is an experiment slightly smaller, like 800 people, but it's dedicated for B physics. Okay. So if you just want to make a mapping, CMS is just like a Swiss Army knife. This is made in Swiss, right? So kind of, or a Swiss Army knife, so can do many different things, but may not be perfect for doing specific tests. So LHCb is more like the art cutter, like these kind of things, right? You can cut something in a pretty way, but they may cannot do many other things. You cannot use this cut or other tools. So I think it's a very nice mapping of these 2 different tool or detector. They are doing different things. CMS is more general, LHCb is more dedicated. So if we really compare the performance, like we line up things. So basically, CMS is designed for looking for barrel. Basically, CMS is like a high PT and looking for more central region of the detection. LHCb is only targeting the forward region. For data set, CMS have a higher luminosity because we want to have a higher luminosity to look for new physics. And that means also dirtier. So dirtier, you need to raise the ratio. The ratio is higher, so efficiency is low. LHCb have like a low luminosity because I want to keep the detection, to keep the background low. So everything low, but the efficiency is high. They try to only zoom in the target region what they want to see. So the analysis strategy of this are all basically similar. We will construct two muons, and normalized to a channel is a so-called normalization channel B plus decay to Z side K plus. And the final analysis is all done with the so-called kind of MDM analysis, a boosted decision tree as a based analysis. This is very similar. And the signal extraction is all done by maximum likelihood fit. And we categorize in the BDT bin. So basically, for each event, we have a BDT value and chart and do measurements. So in the end, the expected performance are very similar for these two experiments, only for this channel. So this is some more comments on how the event should look like. Basically, the signal is a B meson decay to 2 muons. So let's suppose this B meson actually has some finite lifetime, so they will fly a little bit and decay to mu plus and mu minus. So in principle, they become a secondary vertex, which is displaced from the collision point, or so what we call primary vertex or something. And they should form a peak on the mass spectrum, and so forth. For background, there are say for important background, one is like the 2 muons actually can decay from 2 different B, with like one B decay to muon another B. So that was the this is what we call two synaptonic B decays, 2 muons from 2 different B, or one real muon plus one hadron effect to muon, or even they can be something like two double effect, like it's a B to K pi. And there's a K on pi on double effect to muon or decay in the fly, so they become fake muon. So this kind is particularly difficult because this usually peaking, and they are roughly right place. So this is a little bit problematic. The others like if there's 1 muon plus 1 fake, it will be like more smooth distribution. So probably it's okay. So basically, since this is rare, so we need to kill the background as much as possible. So there are many things we can do, like require very good muon, require this vertex to be very well reconstructed, try to reject these kind of things, or try to reject the so-called fake from the isolation, or the direction, should, the B direction and the dimuon direction should match to each other, and so on. So another thing in this kind of measurements, in particular, is that actually we do not know how many B's actually produced. It's not like B factories. We know how many B's in some sense, but here we don't know. So in principle, what we can do is to measure two channels together and take one as a normalization to the other. So so here we pick up the one of the dedicated channel is a B plus decay to Z side K plus. They have actually also 2 muons, so actually cancel many of the cinematics as well in general. For HCP, they also try to use a B to K pi, but in the final combined analysis, we only use a B plus to Z side K plus. Now, and in general, we also check the other channel like Z side phi, which is decay from B sub S. So this is the master formula. I will say this idea like how many signals we have compared to how many signal we got for this control channel, is a normalization channel, correct for all the efficiencies, and also this production for fraction, and so on. So this is what we have. So in the end, we just normalize to this channel and get the output fraction. So another key issue in the measurement is the pi-up. So just for people who do not understand what pi-up usually means, when is in a single collision, we do not have just one interaction, so there should have a lot of interaction in general. Well, we want the luminosity to be high. So this is basically designed for this high PD search, for example, CMS. We want to keep the luminosity as high as possible, so you collect a bunch of the protons and then have a multiple interaction in a single event. So this is a single snapshot, but I see many events are actually overlapping with each other. So in principle, CMS in the average in the previous year with like in each event with like 25 collisions, not just one. And the LGCB try to actually they want to keep a system clean, so they lower down the collision rate to be like 1.7. In this case, they can keep the event clean. You don't see so many things. They only have one or 2 points. In CMS, you see like 25 collisions in the average. So this is how this comes. So, but the trade-off of CMS have a high luminosity, LGCB have a low luminosity. So that's how the scenes can be designed. So another issue is about the background suppression. So just as I say, the signal is small, background is huge. So there are many hidden background, I would say. So not just one sitting in the middle. So even we require 2 dedicated muons, also we already kill many background already, but there's still many things can fall down. Like we are measuring 10 to minus 9, 10 to minus 10. So background is high. So all the measurement actually using so-called boost distributed tree to actually optimize and the separation power from actually many inputs. So just give you a quick snapshot of what is BDT. It's something like this. In principle, you have like a 2 correlated input. You may see, okay, they are signal look like this way, background look like this way. Actually, they are correlated. So if your brain is smart enough, you should be able to say, okay, let me cut along this curvature, right? So if you only look at these 2 dimensions, you don't know. You say, okay, they are mostly overlapped. There's almost no way to do. But here, you can do something like this. So BDT is something like they can try to find this kind of curvature cut by projecting these 2 dimensions into a single dimension, for example, become like this. If you do a chaining and you get this kind of distribution, and in principle we can make a cut like here, cut here, and this cut is actually equivalent to make a cut in 2 dimensions, okay? The curvature. So in this way, you can actually get a much better performance by looking into the individual variables. In this case, we can get the best separation power. Okay, this is basically general for all this kind of so-called multivariate analysis, but we are using BDT here. All right, so before going to the dedicated result, let me just show you one more thing how we really extract the signal. As I already mentioned slightly earlier, that basically we are using so-called BDT to suppress background, but we do not just cut it out. But what we are doing here is like this. We have for each event, we can calculate 1 BDT value. So we get a distribution for signal and distribution of background. And basically, in the data, we don't know which is signal, which is background. So in principle, we just slice. We slice the events in so-called BDT category. That's what we call here. So like BDT bins, 1 bin to n number of bins. So some bins have a very high purity. For example, we see a huge B signal, small background. In some bins have a poor signal to noise. You have a low purity, low signal, high background. And then we perform fits for each category and times all of them together. So in this case, we maximize our so-called separation power and the internal states to get the base signal extraction power. So basically, both CMS and LHC are using similar method based on things like this in general. All right, so let me talk about CMS. So this is a little video about CMS detector. So CMS actually have M is muon. So actually CMS muon is pretty good. So with a muon in the detector NAND. So basically CMS muon system has 3 different devices to a pretty good coverage. So, and in terms of muon resolution, it's also very good, like almost like 1% for the muon massive resolution. So basically, we have 3 ways of reconstruction muon, but you can just imagine that either way you look at the muon at the outer detector, or use the muon in the inner detector only, or you connect them together. So basically, some idea like this. And one issue is about the muon misidentification is that in this analysis, one critical issue is about how do we reject the effect of muons, because just as I mentioned earlier that like BDK to 2 hadrons, they can easily affect to 2 muons. In that case, they form a fake peak under your signal. So how do we reject the effect muon is a very important key factor here. But anyway, so all events have to start with a trigger. So this is a quick snapshot of CMS dimuon trigger. So basically, we have 2 levels of detector. One is trigger. One is local hardware trigger, we call level 1, and the second one is called HLT, so-called software trigger, done with clusters. So this is just almost like a history of particle physics from a very low particle like omega phi up to like depth psi prime. This is dedicated trigger for B, BS, B to mu trigger, and there's a upsilon and the Z, and so far we see no more new things yet. Hopefully we can see something in the next round.
What is the height of your blue shaded BS mean?
This is a dedicated BS trigger. We lower down the ratio to keep more background events.
Yeah, you're saying.
Yeah.
Top height, what does that physically mean?
You mean top 5? You mean this one?
Well, the others are physical, so this is.
This is just like artificial. Because in this region, we lower down the ratio to keep more BS event as well as more background and more signal. So that's why we get the title, the dedicated trigger for this analysis only. Yeah. So others are generic trigger. I mean, this kind of wider thing are generic triggers. So they cover more different things. But for example, like this one is pretty wide, but they basically have no efficiency for BS. Okay. So this is about muon identification. What we do. So generally, the real muon is like this. It's a real muon and production. So they have a track in the inner detector, and basically have no or little energy in the colorimeter, and they go out to the muon chamber. And for fakes, for example, like K-ion or Pi-ion, they can either decay in the middle, like decay to and then it becomes real muon in the end, right? We need that. It's just like this. So this can be a fake muon. Another case like this track actually hit the H tau and produce like a punch through particles. They actually also muon in this case, maybe, and they become a fake muon. So basically, we have ways to reject. For example, like this, we can have a dedicated what we call kink finder to find any non-smoothness of the tracking, or like this kind of kink point, or we can try to reject the muon with more associated colorimeter energy. So basically, we have also many information. Just like some list of information here, we also use BDT here, throw all the information into BDT and make a cut. So in the end, we can actually reject the hadron to muon fake rate to be like 1 to 2 per mil only. So that means like every 1,000 hadron you get 1 or 2 fake muon. That's it. So, but it's still still high somehow. So actually, we want to push it further for the next round. But now it's almost the best we can do. And this is just a quick snapshot of the normalization. Basically, B to Z side K plus have 10 to -3 Benji fraction. So you see big peak. This is a real B plus signal, huge B plus in the barrel and end cap of the CMS. So this is a number of years. They are huge. So in principle, we need to take this into account. And other important factor is the hadronization fraction, which is what we call Fs over U. Basically, this is normalized by B plus. So we need to know how many B plus, the ratio between B plus and B sub S. So this is the factor we actually have to include. And this can be only measured by LHCP so far. So I will not go through detail. It's just like how we suppress the background. In principle, it's just like there are many variables we included, many ideas. And basically, you can see the signal background all looks somewhat different. The dots are basically background, and the kilogram are signal. So we have many different information we can put in. So I just give you a quick snapshot of the variables we are using, and different ideas and different separation power. In the end, we put everything into BDT, and again, make a cut, slice, and fit. So this is how CMS measurement was done. And it's just a quick snapshot of final so-called BDT distributions. So we already have a so-called 4 regions at the beginning, like for different beam energies, and also different detector region already have 4 regions, and we can still slice into more beams. So finally, we get like 12 beams and make fit. So you use this way to get the so-called maximum separation power between signal and the background.
There are no migrations between. You're not afraid of I hate BDTs. But yeah, because I love them. I believe the systematic errors are always under-predicted. So by experimentalists like me. So aren't you worried that you have migrations between these bins because of systematics, or how do you take on this?
But actually, we did the. We cut the sample into 3 actually. One and try to verify these kind of things.